There's a question from David that says, hey, Dr. Hammond, are we having a quiz or anything this week? Yes. We will have a quiz on Friday. My plan is to ask you some questions that involve some of the basics of vectors. So things like, I could in theory ask you anything about like dot product, for instance, okay? And I could ask you at least some basic stuff about the cross product even, although today and maybe a little bit of tomorrow, we'll talk about some applications of cross product stuff. And actually the entire next section is a giant application of both. We're going to talk about lines and planes and in three-dimensional space. And then we'll revisit lines in two-dimensional space and realize, man, I didn't realize we were doing such sophisticated stuff when we were doing two-dimensional lines, but we really were. Okay, so we'll have a quiz on Friday. Again, I have a lot of people in quarantine right now for some reason. So I'm trying to, hopefully, I mean, what tends to happen sometimes is I then get a notification like 24 to 48 hours later that says they are not in quarantine anymore. So I'm hoping that will happen. Hopefully that makes sense. Any other questions? Oh, wait, I'm already recording. Any other questions? Yeah.
I have one small question. We did the matrices yesterday.
Matrices, yeah, we did the matrix. Yeah, right. Determinant of a matrix, yeah.
I forgot how you got the sign.
Well, I mean, for us, for this class, it's fairly simple. Okay, so if I'm like down here, so the question is from Matthew. He's like, how did you determine the signs? Well, for us in the 3x3 case, it's fairly simple, Matthew. It's just, hang on a second, let me fire this thing up. What is happening? I gotta make sure this pen gets engaged. Seriously, okay, there we go. So it's fairly simple in our case. Basically, it just goes, you know, positive with the I, negative with the J, and then positive with the K. That's it, okay? So you just know that the negative term comes with the J component, right? And you kind of see that right here, correct, Matthew, right? You see that negative sign right there? And then you basically just, like if I was doing the J component, you would first attach the minus sign, and then you would cross out basically the second components, yeah? And you would concentrate on these 4 entries right here, and you would do the X thing. Remember that? Okay. And remember, that formula came on the back end of us realizing what the formula was. And we're like, that thing's horrible. Is there a way to remember it? And the answer is yes. It's the determinant of this little 3x3 matrix. Okay. So hopefully that's helpful. But in general, what I said was, suppose I had like a huge matrix that was like 5x5 or 6x6. Then what would I do? Well, you do a similar thing where you kind of go across the first row, or you can even go down, you can go across any row if you want, actually. That's sort of weird. But you can go across, like if you go across the first row, how do I decide which terms come with a plus and which terms come with a minus? Well, what you do is you go row plus column, okay? So like what row and column is that? 1, 1, yeah? Row 1, column 1. What's 1 plus 1? 2. Is that even or odd? Even. Therefore, it comes with a plus. Because basically it's minus 1 to the row plus column. So what about J? Row and column are 1 and 2. What's 1 plus 2? 3. Odd or even? Odd. Therefore, that would come with a minus sign. What about K? Row plus column? 1 plus 3. 1 plus 3 is 4. Even. Therefore, it comes with a plus sign. And that's really helpful because, like this is something you would have to take the linear algebra course to really get into the weeds on. But Turns out I don't have to expand a determinant along like the first row. I could do it across any row or down any column. And there it starts to become a question, what do I put, pluses or minuses on these things, okay? And you kind of circle the entry you're on, you cross out the row and column, and everything else you compute the determinant of. You have to decide whether there's a plus or minus attached, okay? Other questions on some of the basic stuff we talked about yesterday? Okay, remember, when we constructed the cross product, there were three primary things we were interested in. One is that U cross V is a vector that is orthogonal to U and V. What does orthogonal mean again? Basically perpendicular to, okay? So that was the first priority, that we want a vector that's perpendicular to both. But of course, if you just look at this picture over on the left, you can see there are basically two options, either up or down, yeah? Secondly, there's a question about what the length should be. And it turns out a really smart choice is to let the length be the area of the parallelogram determined by U and V, okay? So that area right there, that area is equal to the length of U cross V, all right? But finally, I still haven't figured out what the direction should be. So this is like the second thing, right? The length of U cross V is going to be the area of that parallelogram. And the third thing is direction follows the right-hand rule. So that's kind of the third thing that we want to be true about U cross V, yeah? So remember, you kind of jut your arm in the direction of U, and you rotate it so that my fingers can curl toward the other vector in the direction of your thumb, right? You don't put your thumb in a fist, you kind of point it up, yeah? Or you point it out. After you kind of curl your fingers to the second vector, wherever your thumb points, that on your right hand, that is the direction of U cross V. Okay, so for instance, let me draw a picture of an arm here. So like if I'm doing U cross V, then I would put my arm in the direction of U, and I would curl my fingers. I would rotate my arm so that my fingers curl toward V, yes, so they're kind of curling toward V. And then which direction is my thumb going to point then on my right hand? Up. Don't you see? Yeah, it's kind of pointing up, yeah? All right. Now, what if I were to do V cross U? Well, in that case, here's my right arm, okay? I would kind of have to rotate my arm so that my fingers can curl over there, yeah? Okay, and in that case, here's my fingers curling, okay? And where's my thumb gonna point now on my right hand? Down, don't you see? Yeah, so here are my fingers are curling from V toward U, and now my thumb points down. So that's why this thing points in a downward direction. Okay, so V cross U. You kind of read these vectors from left to right. Okay, there you go. That's my kind of attempt at drawing a picture. It's kind of a mitt-looking hand, but you know what I mean, I think, right? Supposed to be some fingers in here. Oops, I just erased it. Hang on, I think I can undo that. Yes, I can. Okay, let me put a couple fingers in there. Put a couple fingers in here. This is time well spent, okay? Any questions on that? So first, I want the thing to be perpendicular to both U and V. Second, I want the length to be the area of the parallelogram determined by those. And third, the direction of that thing is determined by the right-hand rule, okay? And taking all of those things into account, we ended up coming up with a whole bunch of formulas, or things that had to be true about the cross product. In particular, we figured out that the length of the Cross product is given by length of u, length of v, sine of theta, by just thinking about the area of parallelograms, the height and the base. We figured out that the cross product of two vectors is equal to the opposite of the cross product taken in the opposite direction. We figured out that u cross v is 0 precisely if u and v are parallel, yeah? If the one is a scalar multiple of the other, because then the parallelogram is degenerate, right? You understand what I'm saying here? If the vectors are scalar multiples of each other, I have a degenerate parallelogram, which means a 0 area parallelogram, which means a 0 vector, yeah? Because after all, the length of the cross product is equal to that area. Okay, so that made sense. So that's interesting because there's a nice analogy with the dot product, correct? The dot product being 0 meant that the vectors were perpendicular, unless one of them was 0. The cross product being 0 means the vectors are parallel, yeah? So there's a nice analog going on between those two. They're analogous to each other in that way. And of course, we also know that, like, if I take the dot product of u and v, that's the length of u times the length of v times cosine of the angle between. So that's another nice analogy with cross products and dot products. The length of the cross product looks like the dot product, except cosine has been swapped for sine. This is a pretty basic fact. Basically, take a scalar times u cross v. It's the same as taking that scalar times u and that scalar times v. Basically, this has to do with stretching one side of the, right, like CU and CV. That's like stretching one side of the parallelogram. Do you see what I'm saying? Stretching one side of the parallelogram, I'm going to have to scale u cross v by the same amount to preserve the area. Yeah. Okay. This guy down here is basically the distributive law. You can work this out based on geometry as well. U cross v plus w. Oh man, I like to draw this picture, but I feel like I always mess it up. I want to try to draw the picture. All right, so just bear with me. So u cross v plus w. Okay, so suppose this is v, and suppose this is w. Right, so this is w. And where is v plus w? Well, it's right here, okay? Okay, so there's v plus w. Okay, and where is u? Well, I need to draw it, all right? Okay, so here's u. Okay, I really like drawing this picture. It's kind of a cool picture. So think about this for a minute. U cross v plus w is going to be, like the length of that is going to be the area of this parallelogram that I'm kind of drawing in right here, yeah? So in other words, let me kind of highlight this in yellow. Okay, so that right there, that is the length of u crossed with v plus w. Okay. Now, what about uv? Okay, so this is interesting. So, what about uv? Let me use some. I don't know. Let me use blue again. Okay. uv. Okay, so I would have to do what I just did there. Okay. uv, u cross v. I would have to kind of draw in this parallelogram, okay? Okay, and then UW is this guy right here. So here's UV. Let me use some different colors here. I'll use green. UV is this area right here. So this is the length of U cross V, okay? And now I'm going to use, I guess, red or something, just so I can make this stand out. Okay, so this guy right here, what's that? Well, that's U crossed with, that's the length of U crossed with W. Now, why is the green plus the red equal to the yellow? The green plus the red is the same as the yellow because do you see those little triangles made by V, W, and V plus W? I mean, after all, this right here, let me just say, this right here is really just V again. This right here is really just W again. And this down here is V plus W. So you see that yellow triangle and that kind of green and red triangle up there formed by VW and V plus W? That's the same area, isn't it? And therefore the yellow stuff is equal to the green stuff plus the red stuff. Yes? You see what I'm saying? Okay, so that's kind of cool. And that's why this property right here actually holds. U cross quantity V plus W is the same as U cross V plus U cross W. We're seeing it in terms of area, but we can actually see it as a vector as well. It makes sense in terms of area, but we actually see it as a vector as well. Okay, well, and then U cross zero vector is just the zero vector. And that makes sense to us because if I try to compute the area of a parallelogram where one of the vectors determining it is the zero vector, that's a degenerate parallelogram. Yeah. Okay. So yeah, and then we went through, if you'll recall, and we actually computed what the cross product of all the basic standard vectors would be. I cross I, J cross J, K cross K, etc. And then we said, okay, let's use these things to figure out what a general formula would be for the cross product by using all of those properties above. And that's where we came up with this really cool formula for the cross product. Yeah. And we used that to compute some cross products, like if I had U equal to 1, 2, 3 and V equal to negative 1, 2, 4, we computed U cross V. We did this problem right here with points that were determining a plane, okay? And we sorted out, we said, okay, if I want a vector that's perpendicular to the plane determined by these points, what I can basically do is create two vectors and compute the cross product. And that would give me a vector that's perpendicular to the plane. Yes, Jerry.
So in like the big list where J equals negative,
Uh-huh.
so like I get like why like the sign thing of inside and
Yeah.
outside. What was it that made like the full J negative?
Outside what?
So like you have like positive I, negative J, and positive K. I understand why there's a like each with minus the terms in the inside parentheses. I remember why the J was negative compared to the I. Like I is positive and K is positive, like you could negate all the J terms.
Well, yeah. So I mean, I didn't have to put this negative sign. I didn't have to pull it out. But the kind of the motivating factor for as far as the formula is concerned is you always kind of want. So look, you have the first vector here, U1, U2, U3. Do you see that? What you kind of want to have is consistency in terms of how the formula works. You want the first term you want the positive term to have like the lowest, you want to have like the lowest indexed, like the earliest coordinate from the first vector. So for instance, this guy involves U1 and U3 from the first vector. Does that make sense? If I were to distribute that minus sign through, I would have like U3 V1 minus U1 V3, which that would mean that my coordinates were kind of like out of order from that. So that's just, the only reason you do that kind of in the formula itself is one, it kind of works well with the matrix, but also it's consistent in terms of like in the first part of this, do you see like I have second coordinate of U and then the third coordinate of U? Here I have the first coordinate of U and the third coordinate of U, so they're kind of in order every time, yeah? And this one I have the first coordinate of U and the second coordinate of U. Does that kind of make sense? That's kind of a motivating factor for having that minus sign there. All right. All right, so I want to do something else geometric. So do you remember this? By the way, so we went like this. We said, okay, suppose this is the point 114. Suppose this is the point 439. And suppose this is the point 2, -1, 10. Okay, I'm going to form these vectors. And by the way, all of this is happening in like a plane. Yeah. Okay. And we called this vector right here U, and this vector V. And we computed them right here. So U is 4 - 1, comma 3 - 1, comma 9 - 4. When I look at the differences in X, Y, and Z coordinates. Okay, so that gives me this. And then V is, 2 - 1, -1 - 1, and then 10 - 4, which gives me this. And then, of course, if I do U cross V, that is going to be a vector perpendicular to the plane that those points live in. Yes? Okay? Because that vector is perpendicular to both U and V. And yesterday we talked about the direction U cross V would have. Which way, I mean, this picture might not be accurate, but which way would U cross V point? U's kind of going into the board, yeah? Put your arm in that direction, rotate your arm, curl your fingers towards V. My thumb points down, yeah? So it would be like this. So this would be U cross V in this particular case. Okay, it's just, I'm just trying to make sure we're on top of things geometrically, okay? All right, so what if I asked you to find the area of the triangle determined by those 3 points? Well, what do you know is true about the area of the parallelogram determined by these 2 vectors? What's that given by? What's the area of that parallelogram given by? The length of U cross V. So that area right there is going to be the length of U cross V. So I ask you, please help me. What if I were to restrict to just the triangle determined by those 3 points? What about that? What do you guys think? Yeah, just half. Just half of that, which is exactly what's going on down here. I want to find the area of the triangle determined by those 3 points. You would compute the length of U cross V, which is the area of the whole parallelogram. Okay. If you do the math, you get square root of 717. So the area of the triangle is just half that, half the square root of 717. Yeah. So the cross product is paying good dividends to us geometrically for sure. Okay. All right, let's look at something else that's kind of an interesting little factoid. This right here, this picture is a parallelopiped. Okay, that's kind of a fun word. Okay, it's called a parallelopiped. What you do is you basically take 3 vectors, draw them emanating from the same point, and those 3 vectors form kind of one corner of a parallelopiped where I just jump around. And like, for instance, this guy right here, all these green guys that I'm drawing right now are all basically W, yes? Okay, all the blue guys, okay, okay, right? All these blue guys that I'm drawing right here are basically just copies of U, yes? And then all of the red guys are copies of V. You kind of just jump around and form this little parallelopiped. That's kind of exciting, yeah? I think that's pretty exciting. You can almost see, look how cool this is. You see the green things kind of going around in a little circle or like a circuit around the edges. Same thing with the blue and the same thing with the red. And you form this thing called a parallelopiped. Now, how could I use cross products to compute the volume of this thing? Well, it might be surprising to you that, that we can actually do that, okay? How can we do that? Well, first of all, let me just say, the volume of any sort of geometric shape like that, where all the sides are parallel, is basically just going to be the area of the base times the height. That's going to be the area of the base times the height. Well, what is the base of this parallelepiped? What is that? Isn't the base of this parallelepiped just determined by U and V? Yeah? Okay. Okay, so the area of that base is given by the length of U cross V. Right? We use the cross product to capture the area of parallelograms determined by vectors. Yeah? But then I also need the height. So the area of the base I can get my hands on pretty easily, but I also need the height of this thing. Okay? And to do that, we have to work a little bit harder. Okay? First of all, U cross V, is it clear to you that, okay, is it clear to you, first of all, U cross V is pointing in this direction. Why? If I put my hand out towards U and I wrap my fingers towards V, the arrow points up in this case. Yes? Okay? So U cross V is pointing in the direction that I've indicated there. Theta is the angle between U cross V and that other vector W. We already know what the angle is between U cross V and V. What's the angle between U cross V and V? I'm not trying to trick you. What is the angle between U cross V and V? 90 degrees. Exactly right. Okay? And same thing with the U cross V and U. But the angle between U cross V and W, that's a little bit more mysterious. So we label that angle. And we need to know the height. Okay? We need to know the height of this parallelepiped. And we can actually use, this is amazing, you can use U cross V to kind of sort that out. Okay? Now what you can do is you can kind of project this thing over to here, and you get a little right triangle. Okay? And you get this little right triangle. And what we really need to know is this distance right here. That is the height of the parallelepiped. And let me ask you, look at that right triangle over there. That basically arises from projecting W onto U cross V. Which trig function is going to let me get my hands on that height? Which trig function? Cosine. You know that cosine of theta is equal to adjacent, which is h, over the hypotenuse, which is the length of W. Yeah? So in other words, the height is equal to the length of W times cosine of theta. That's amazing. So that's where this formula comes from right here. Okay? Length of U cross V times length of W cosine of theta. And then you say to yourself, oh my goodness. Length of one vector, length of another vector times the cosine of the angle between them. I've seen that before. What's that? Length of one vector, length of the other, the cosine of the angle between, dot product. Yeah? So amazingly, that ends up being the dot product of U cross V and W. Now, it could have been that the cross product actually flipped the vector down, okay, even if you used V cross U or something, in which case you would have gotten the negative of the answer you would have wanted, okay? But the volume will always just be the absolute value of this dot product. That's amazing. This is actually referred to as the scalar triple product. It's an amazing little geometric fact here. It's a combination of the cross product and the dot product. And in the end, it gives us the volume of this three-dimensional parallelepiped determined by U, V, and W. I think that's cool, but, you know, I just do. So any questions on that? Any questions? Well, so look at this. Let me just say, oops, not negative of the area. What do I mean here? If I would have taken V cross U, I would have gotten the negative of the volume. Okay, I would have gotten the negative of the volume of the thing. So, but always absolute value of this thing would give you the volume of that parallelepiped. Okay. So W dotted with V, U cross V, or U cross V dotted with W, that's called the triple scalar product, or sometimes people like to say scalar triple product, okay? And it's essentially a way of combining the cross product with the dot product. And the result is a scalar, yes? That's why it's called the scalar triple product, okay? So watch what happens if I actually multiply this out, okay? Or if I actually do the dot product of U cross V. Dot product of W with U cross V. So I just write W as W1, W2, W3. I know that to compute the cross product, I have to compute this determinant of this 3x3 matrix, okay? Which basically amounts to kind of crossing out the first entries for the I component and computing that little X thing, yes? And then negating the same thing here, and then this thing here, yes? Okay? And watch, if I were to take the dot product, W1 would get multiplied by this thing. Then I would have minus W2 times this thing plus W3 times this thing. But it feels to me like I'm almost doing I, J, and K times, like that's kind of what I did with I, J, and K before, wasn't it? I was in the place of W1, J was in the place of W2, K was in the place of W3. So actually, in the end, if I want to compute the scalar triple product, all I have to do is like replace IJK with W1, W2, W3 up here and compute the determinant that way, and it will actually work out nicely. Okay? So basically, scalar triple product, which computes the volume of that parallelepiped, is going to be given by just simply replacing IJK and that 3x3 determinant with W1, W2, W3. Okay? All right. Any questions on that? That's sort of some cool geometry. Just wanted to make sure it's clear to everybody. So any questions? So here's something that's pretty useful. Suppose the scalar triple product is 0. What does that tell you about the volume of the parallelepiped? Remember, the scalar triple product will give you the volume, yes? If the scalar triple product is 0, what does that tell you about the 3 vectors? Well, it tells you the volume of the parallelepiped is 0, yes? Which means that W vector up here, it's not really like out of the plane of U and V anymore, yes? It must be in the same plane as U and V, yeah? So what's going on here is the parallelepiped is collapsed and UV and W are in the same plane. So if the scalar triple product of 3 vectors is 0, what can we conclude about those 3 vectors? They all live in the same plane, yes? Right? You don't have a situation where 2 of them are in one plane together and the other one's like out of it or something, yeah? Okay. Scalar triple product 0 means UV and W are coplanar. Okay. Find the volume of the parallelepiped determined by U equal to that, V equal to that, and W equal to that. Look, this is just baby food, okay? Once you know the formula, it's easy. All you do is you just straight put the things in the matrix, boom, 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 and you compute the determinant. That's it. We've done all of the thinking at this point. And at this point, it just becomes very formulaic. So it's going to be U dotted with V cross W. It doesn't really matter how you do this. Like I could do V cross W and dot it with U. I could do U cross V and dot it with W. Okay. It doesn't matter how it plays out. You just have to make sure you dot one of the vectors with the cross product of the other 2. Does that make sense? I just have to cross 2 of the vectors and compute the dot product with the third, which is kind of weird because what that tells us is it doesn't matter how we shuffle these things around. Like if I go U dotted with V cross W, it's got to be the same thing up to a sign change, right? It's got to be the same thing as like V dotted with U cross W, for instance. Isn't that kind of sort of surprising? Apparently, since it's all tied to the parallelepiped, and they have to be giving the volume plus or minus of that parallelepiped. Shuffling things around shouldn't matter. So what I'm saying is this should be the same thing as, V dotted with U cross W, okay? And it should also be the same thing as what? I don't know, W dotted with U cross V. Okay, with one caveat, what might I have to do just to make sure we're on the same page? I might have to take absolute values of things, right? I might have flipped the sign of something because of the way that cross products work. So let's compute this. How do I do it? Well, you go 1. So let me just make sure you understand this. I go 1, and then I cross out its row and column. And I get this little 2x2 thing that I have to compute the determinant of, yes, okay, which is where this first thing comes from, okay. And then what do? Well, next, I do 4, except what does 4 come with? A negative sign, okay. And I cross out its row and column. And now I have this little 2x2 that's left, okay. Okay, that's where this second thing is coming from here. Okay, and then lastly, you go 6, cross out its row and column, and you have this little 2x2 left, which is where that third term is coming from. Okay, yeah. So then what? Then you do the little, X thing on each one of these. So it's 3 times 5, 1 times 3 times 5 minus negative 2 times 1, yeah? 3 times 5 minus negative 2 is 17. And then I go negative 4, and what am I going to get here? 2 times 5 is 10, minus negative 1 times 1. So that's 11, okay? So it's minus 4 times 11. And then finally, you go 2 times negative 2, which is negative 4, minus negative 3, which is negative 1. Which is where that third term is coming from. 17 minus 44 minus 6 is negative 33. And you say, hey, I thought this was supposed to be volume. Well, what's the true volume then? What's the volume equal then? If I get negative 33 as a scalar triple product, the volume is 33 cubic units, whatever your units are. Okay? Are U, V, and W in the same plane in this case? Absolutely not. What would I have gotten if they were in the same plane? 0. You would have gotten a volume of 0 for the parallelepiped. Okay? All right. One more thing. I want to talk a little bit about torque, and this will kind of bleed over into tomorrow a little bit. Okay? I know that you've heard the term torque before. Okay, but I want to talk about it in a little bit more detail than perhaps you have in the past. So here is a little, I put some pictures in here, which I think are pretty cool. As I literally was doing this the other day, okay? I just think it's funny. It says use foot, right? Okay, and when you generate force around kind of like a central point, like rotational force around a central point, you're talking about torque physically, yeah? Now, how can we measure torque in some kind of meaningful way? Well, what you do is you basically have one vector that emanates from the point of rotation and goes out to the length of the the length of the object that you're using to apply force to, okay? So typically you use R, oftentimes this is so stupid, but in my mind, when I see R, I think wrench, okay? I know that's not how you spell wrench, okay? But R is typically used to represent the wrench itself, with the point of emanation of that vector being the point of rotation. Yeah, so the vector comes out of that and it goes along your wrench, and the length of that vector is basically the length of the wrench or the object that you're using to apply pressure to. And then you have a force vector, okay? And the force vector is coming from you applying force to that wrench or whatever the object that's exerting rotational force is, yeah? Okay? And then the question is, how much force, how much rotational force is actually being generated by this thing, yeah? And one way that you can measure that is by the area of the parallelogram determined by the force vector and the wrench vector, yeah? Because look, the most force that I'm going to get is if that force vector is going straight down perpendicular to the wrench. Does that make sense? And that's literally going to be the most force that you can get. I mean, if I were to take that same force and like an idiot, like rotate my foot so that a lot of the force is just going, is not really working in the direction perpendicular to that thing, I could capture that by sort of tilting that parallelogram, yes? And the area would be smaller then, okay? So this area is actually going to be a measure of how much force, the area of the parallelogram determined by these two things, is going to measure how much force is being exerted at that point of rotation, okay? So here's another picture, like, you know, I almost like to think of F as being back here though, okay? So here's F and this angle theta right here, yes? And what I'm saying is, you know, what is the height? What is the height of this thing right here? Well, it's going to be the length of F times what? On the opposite side. So it's the length of F sine of theta, yes? And so the area of this parallelogram, which overall measures the amount of force being generated at that point of rotation, is given by length of F sine theta times the length of R, yes? So it's going to be length of F sine of theta, that thing multiplied by the length of R. Okay, there's more, you talk about more sophisticated things in physics, like you talk about angular momentum and things like that. But in the end, what's really going on here geometrically is the area of this parallelogram is determined how much rotational force is happening there. And it makes sense that that would be the case. The stupider I am with that force vector, in terms of not being perpendicular to the wrench vector, the worse off I'm going to be. I'm going to get less force that's generated. But this is just the length of, do you see? This is the length of R crossed with F, yes? And this vector right here is often referred to as the torque vector, and the Greek letter tau is often utilized for that, okay? So the magnitude of the torque, so this torque vector is defined to be your wrench crossed with the force vector applied to that wrench, okay? So that's the torque vector. The magnitude of the torque is a measure of how much rotational force is being applied at this point right here, at the point of rotation, okay? So there's the torque vector, distance vector indicating the direction and distance from the pivot to the point where the force is applied. You have the cross product, and then, oh, and by the way, it's not just the wrench, it's where you apply the force. What would be really stupid is if I, like this bar right here, what if I put my foot like way back here? Does that make sense? If I put my foot way back here, that would be pretty stupid also. That would change my wrench vector to that tiny thing. Does that make sense? So that's what I mean over here when I say it's the distance vector indicating the direction and distance from the pivot, that is the point of rotation, to the point where the force is being applied, yeah? And then I have this force vector. which is literally the force that I'm applying. Okay. Here's a little picture of things. You know, there's the torque vector R crossed with F. If you think about it, R crossed with F, the torque vector points up in this direction. Don't you see? I mean, think about it. I do the right-hand rule, R crossed with F, right? Remember the torque vector is R crossed with F, correct? Okay. And this thing would be pointing up in this little scheme that I have going on right here. Yeah. Any questions on that? Oh, and by the way, let me go back over here before, just one last little tidbit. We'll do some examples of this later. R crossed with F. So think about it. If I translated F back here, R crossed with F, put your arm toward R, and then rotate your arm so that your fingers can curl toward F. Which direction is the torque vector going to be coming? This way. Right, so this right here, right? So this would be the torque vector. The torque vector, of course, the formula is R crossed with F. It would be that way. Your thumb is pointing out away from the wheel, yes? Okay, which is interesting. That's the typical situation that you're going to find when you're dealing with torque. We'll do an example tomorrow, but I just wanted to lay the theoretical framework. Okay, that's it.